order to determine which is the best in particular case, we have to cover the at least these topics here. The first we will discuss the coefficient quantization, and then we will discuss about the here the signal quantization, dynamic range scaling, and the limit cycle. First is the coefficient quantization. If we are interested in order to quantize the filter that has to be implemented, what is the meaning of the quantization? Means we are trying to shift the information from the infinite precision to the finite precision. And what is happening in this particular case, whatever is the coefficient that has been represented with an infinite number of the bits, that has to be represented with the help of the finite number of the bits. So naturally what will happen, the value of the coefficient will be changed, and hence we can say the filter which we implement is not exactly the SZ, that is the system function of the filter that has to be designed, but it will be modified by the H cap Z here, that is the modified SZ, which we hope is closer to the SZ. And as it is closer to the SZ, so better will be the designing here, better will be the quantization concept here. But if we are trying to exactly achieve the same performance as in the case of the SZ, it will be more and more here the complex and the costlier. So there is a need of the trade-off between the coefficients of the SZ and the H cap Z here. We can check whether the H cap Z meets the control designing. Control designing means whether the stability region remains same, or due to the change of the coefficient, the stability is changing. If there is any type of the doubt or any type of the possibility to change the stability of the filter to unstable region, then there is a need of the modification here. And the structure of the here the structure of the filter network has a drastic effect on its sensitivity. As we know, if the order is higher, then what will happen? It will be more and more sensitive towards the here the coefficient quantization error. And so that higher order has to be broken into the smaller order, like the first order and the second order section. Specifically, it will be broken into the second order section if the order is not odd. Now the signal quantization, here the whatever the signal has to be processed, that has to be processed through the finite precise arithmetic here the and the computational elements. So there is a need of the signal quantization, and at the same time there is a need of the representation of the dynamic range. Here, what is the dynamic range? Dynamic range is the value, that is the ratio of the maximum value that can be represented to the minimum value that can be represented by a finite set of the numbers, or a number of the bits, or with help of the word length. So here the third F is the dynamic range scaling, and the fourth one is the limit cycles. In the limit cycle, what is the limit cycle? If the filter that has to be implemented is subjected to the zero input, or the fixed input, or the constant input, even then we are getting here the output, oscillating output, then that is effect is known as the limit cycle effect here. Now, and this naturally these effects takes place due to the here the quantization here. Now if we see here the coefficients will be represented with the help of the bits here. So we are just trying to represent, we are trying to cover the effects of the different type of the representation of the coefficients. And as we know, the coefficients can be represented either using the fixed point representation or the floating point representation. Now, if we consider any number that has to be represented in the binary form, having the b plus 1 bit, then this can be represented in the arithmetic form. This may be represented something like in this manner. That is, the if x is the value, and that has to be represented by the finite number of the bits, that is the b plus 1 bits, then that value will be modified at the s cap, and it will become here the whatever is the maximum value of the x multiplied by minus b naught plus summation. Then b plus 1 is the total number of the bits, and bi are 2 to the power minus I, and this may be represented as the whatever is the maximum value of the x multiplied by the xb, that can be represented with the finite number of the bits here. Now, if we see, if we are trying to represent the here the xb with the help of the b bits, b plus 1 bit, that is the starting from the b0 to the here b0 to the vb, that is the total number of the bits that are required here are the b plus 1. This is the representation of the general word length here. Now, if the b naught is 0, then the range of the modified number, it will lie between the 0 to xm multiplied by 1 minus 2 to the power minus b. And if b naught is 1, then the modified value of the x, this will have a range of the minus xm to the 0, because it will be multiplied by the in the range of the minus 1 to the plus 1 here. Now, the step size, what is the step size? Whatever is the total value, that will be divided by 2 to the power b. That is the here the step size will become the xm to the power minus b, and this will be represented as the delta. As we have gone through this concept in the PCM, pulse code modulation here, and if the fixed point conversion, we are interested in order to calculate the fixed point conversion error. That is, we are using the number of the fixed bit, so the error will become here the xm multiplied by the value of the xb, that is the modified value of the x minus the original value of the x here. This will be the conversion error. For 2's complement, the conversion error range will be from the step size, that is minus of the step size, to the 0 here. And in the 2's complement rounding, if we are using the truncation, then the range of the error will be minus delta to the 0 here. And if we are using here the rounding, then it will lie between the delta by 2, that is and the error will be less or equal to the delta by 2 here, that is minus delta by 2 the plus delta by 2 here. Floating point arithmetic splits the b plus 1 bit. As we know, if we consider the floating point, then we have to consider the two sections. One is the exponent, second one is the mantissa. And this modified value may be represented something like in this manner, that is the modified value of the x, that is the x cat, will be m times 2 to the power e, where the range of the m, that is modified, the magnitude of the m will be minus 1 to the plus 1 here. Now, the exponent basically allows moving the decimal point, means what will be the location and position of the decimal point, that will be decided with the help of the exponent here. So if we again come to the here the mathematical operations using the floating point arithmetic, then we will find that it is much harder to implement, because hardware implementation requires significantly more logic than the fixed point implementations, and the software implementation requires significantly more operations, so run much more slowly on the same processor. But at the same time, here the floating point with a fixed point number of the bits, floating point representation allows much greater dynamic range. Dynamic range is better in the case of the floating point. And what is the dynamic range? As we have discussed, dynamic range is the ratio of the maximum value that can be represented with the finite number of the bits to the minimum value that can be represented by the same number of the bits here. Now, the floating point arithmetic, see here, the floating point arithmetic, there is a question. Floating point arithmetic, although much harder to implement, poses less of the problem to the digital filter designer than the fixed point arithmetic 5. See here the example. If we consider the multiplication of the two numbers, that is a 13 by 16 to 9 by 1 to 8, 13 by 16 may be represented as the, this one is that is a 8 by 16 or the 1 by 2 plus 4 by 16 or 1 by 4 plus 1 by 16 here multiplied by 2 to the power 0. Similarly, the here this may be represented as the this is the 1 by 16 and this is 8 by 16, that is 9 by 16 multiplied by 1 upon 8, that is 2 to the power minus 3. This is the floating point representation, and this is the fixed point representation here. Now multiplication. Now if we use the fixed point representation, then the product will be represented by these number of the bits here, and float in the case of the floating point, this is the here the result due to the floating point. Now see what is the effect. See the comments here. To store the result without losing precision, fixed point requires how many bits? That is the 12 bits, but floating point requires 11 bits here. So generally floating point results will be much better than the fixed point results. Double precision math almost never gives the problem to the control designer. If we are using the floating point, naturally the results will be better, and if the results are better, then naturally there is less problem of the stability of the control designing here. So due to this reason, what happens, the hardware DSP chips exist with the floating point arithmetic built in. But during the time of the implementation, when we have to select the fixed point representation here, because it is easier to implement here. The direct form now it be considered here the first concept of the trade-off, that is the coefficient quantization effects. As we have discussed, in order to consider the trade-off, we have to cover the four concepts. The first one is the coefficient quantization effects, and the second one is the second signal quantization effect, and the third one is the limit cycle oscillations. Here we are using the coefficient quantization effects, the direct form implementation of the second order system. Why we are considering the second order system? Because we have discussed that first we will discuss about the second order system and the first order system. As we know, if the order is higher, it will be more and more sensitive to the coefficient quantization error. So we will discuss about the first, and that higher order has to be broken into the first order section and the second order section. So we will discuss about the first order section and the second order sections implementation concept. Now, if we consider a transfer function of the first order section, say the Hz, and that is the direct form. This may be represented as the bk z power minus k summation k equal to 0 to n divided by 1 plus summation k equal to 1 to n a k z to power minus k. Yeah. And we have to use the AKs and BKs as the coefficients here. And to realize this system, we need to quantize the coefficient AKs and BKs with the finite number of the bits here. So due to this finite number of the bits, now say the coefficients has been quantized and the value of the coefficient has been modified as the VK cap and the AK cap. So now we will get a new modified transfer function, that is the H cap Z here, and we are just moving to this concept in order to describe the differences between the Hz and the H cap Z. Since the Hz has the different value than that of the H cap Z with the different coefficients, so what will happen? The position of the poles and zeros and the values of the poles and zeros will be also different than that of the Hz. And how the zeros will be obtained by factorization of the numerator, we can get here the zeros here. Similarly, by the factorization of the denominator of the modified Hz, we can achieve here the poles of the system. We see that the position of one particular zero is affected by all the coefficients of the BKs. BKs are in the numerator, so if there is a change in any one coefficient, it means now all the zeros will be affected by that change here. Similarly, if we are trying to change any one coefficient in the denominator, then all the poles will be affected by that change in the AKs here. Thus, the effect of the quantization is in quantizing a specific coefficient is not isolated in any way, but affects all poles and zeros in the function. If we are trying to change any one coefficient in the numerator, then all the zeros will be affected. Similarly, if we are trying to change or if there is modification in the coefficient of the denominator, then all the poles will be affected by that variation or that modification. Now, a non-obvious result which may be obtained with the little math is that closely clustered poles and zeros are more affected. Thus, what happens? What is the meaning of this one? That is the narrow band filters, narrow band low pass and the high pass filters of any sort will be mostly strongly changed. They will be more affected by the quantization. Which type of the filters will be more affected? Naturally, the narrow band filters will be more affected by the quantization. So what we do about this one? We try to control the effect of by localizing it using the parallel and cascade form. Suppose we are using the parallel realization and the cascade realization, then what will be the effect on the quantization here? As we know, cascade and the parallel form implementations are made up of sections of the cascading or the parallel combination of the second order, as well as if there is a need of the first order and direct form filters. Thus, in to be able to see how the coefficient quantization affects, first of all, we will try to cover the second order section here. Now, if we consider any second order section, say Sz is given upon 1 minus r e to power j theta z to power minus 1. That is the first section. Similarly, the second one will become here the 1 minus r e to power minus of the j theta j to power minus 1, having the complex poles. And now this may be represented as 1 minus 2 r cos theta z to power minus 1 plus r square z to power minus 2 here. Now, if we see, then the structure can be modified something like in this manner. That is, these can be realized by the filter form on the right side. That is, the xn is the input, and this is the first delay z to power minus 1, z to power minus 2. This coefficient is the 2r cos theta, and the second one is the minus r square related to the z to power minus 2 here. Now, if we see, then we will find the why do we quantize the r cos theta and not the 2r cos theta? The multiply by the 2 can be performed exactly by a shift register. If we are trying to multiply the 2, then it means we are trying to shift the value with the help of the shifter or the shift register. Now, if we see here, to see which poles can be implemented by this structure using the fixed point arithmetic, suppose that 4 bits, we are using the 4 bits. So how the 4 bits will be represented? 4 bits in fractional form may be represented something like in this manner, that is the 0.001, and the second one will become the 0.0010. Similarly, there will be the 8 combination here. So r cos theta can take on these 8 values, and so can the r square also here can be represented with any one combination of these representations here. Now, if we observe, then we will find that the narrow band low pass and the narrow band high pass filters are most sensitive to the coefficient quantization and thus require more bits to implement. In order to reduce the here the sensitivity towards the quantization error, we have to increase the number of the bits during the time of the representation. Since the narrow band low pass and the narrow band high pass filters are most sensitive to the coefficient quantization, thus there is a need to include more and more bits during the time of the implementation. Sampling at too high a rate is bad, since it pushes poles closer to the +1, and if it is closer to the +1, it means the implementable poles density is where the implementable pole density is smallest. So in this smallest pole density range, we will try it to avoid this region here. So the too high rate of sampling is also avoided. Sensitivity increases for the higher order direct form realization. That's why what happens, the higher order direct form are broken into the first order section and the second order section here. Now, what is the solution? Rather than implementing the second order section, that will be broken into the first order section and the second order section, in order to avoid the sensitivity as well as to design more and more controlled system here. Now see here, if we are also interested in order to here they avoid this type of the quantization effect, then all of the coefficients of the network will be in the here the form of the pair. And what are those pairs? That is the r cos theta and the r sin theta. This will be a modified structure that avoids the effect of the quantization here. Now the same second order section, in which in the previous one we have used the r cos theta and the r square coefficient, but now we are using a combination of the r cos theta and then here the r sin theta, and then again delayed by here the one delay, then this will become the minus r sin theta, and this will become the r cos theta here. Now this will be the more here better design, that is having the lesser value of the quantization error here. Now if we see here the architecture, then how the quantization error can be reduced using the different type of the architecture here. Say if we use the we are trying to analyze the coefficient quantization error in cascade and parallel form implementation. Cascade and the parallel form realizations consist of the combination of the second order direct form systems. However, in both cases, each pair of the complex conjugate poles is realized independently of all the other poles. Thus, what will happen to the error? Error in a particular pole pair is independent of its distance from the other poles of the transfer function. Then what is the effect of this one? For the cascade form, the same argument holds for the zeros, since they are realized as independent second order factors. So the cascade form is generally much less sensitive to coefficient quantization than the equivalent direct form realization. If we are using the cascade form realization, that will be less sensitive towards the coefficient quantization error. The zeros of the parallel form functions are realized implicitly here, that is, they result from combining the quantized second order sections to obtain a common denominator. So what will be the effect? A particular zero location is affected by quantization errors in the numerator and denominator coefficients of all the second order sections here. Now if we see the DSP processing, then the DSP processes the real life signal. That is, real life signal has to be converted into the digital form with the help of the A to D, and then after processing, that has to be again utilized in the real life. That is, there is a need of the D to A conversion here. So A to D and D to A signal quantization effects have also to be analyzed here. If we consider here this one, that is the 16-bit A to D converter and the 16-bit D to A converter, but there is a need of the 32-bit DSP processor, because during the time of the multiplication, if the two informations or two data are there having the 16-bit, then naturally the product will be at least 31-bit here. So the 32-bit DSP processor will be utilized for this one. Now, if there is a need of quantization, and there are the three different ways of the quantization. One is the rounding truncation using the tools, complementation truncation using the sign and the magnitude here. But the rounding is the most common, as it generally gives the best results here. And in the rounding case, this is the description here. What is the range of this one? Now, in order to describe this one, if we consider here if we choose the xm, that is the maximum value of the signal that has, or the value that has to be quantized, is the xm, and based step size based on the variance of the input signal, and we assume that xm is the 4 type of the here the sigma, and the variance is the sigma square with the zero mean. We can also use here the xm as the 3 sigma or the 5 sigma. If we assume the 4 sigma, then this is known as the 4 sigma scaling. We are using the 3 sigma. This is the 3 sigma scaling. If we are using the 5 sigma, then 5 sigma scaling is the name given to this type of the scaling here. Now, if we will try to analyze this one, that is the xm is 4 sigma, and we will try to analyze what is the overload region and what is the granular region of the error here. And this middle one is one is the granular region, and the towards the right side and the left side, this one is the overload region here. Now, if we are interested in order to analyze the quantization error, that is represented as the En. En is the error. Error is nothing but it is the difference between the actual value and the quantized value. So here, if the Xn is the actual value and Xcnt, that is the quantized value, then En will be a difference that is represented by this one. It means if we are interested in order to represent the Xn, then Xn is nothing but the Xcnt plus En. This is the model of the representation of the error signal due to the quantization here. Now the En, in the case of the rounding, this may be represented in the random process having the probability density function, that is 1 by delta, and the range is from minus delta by 2 to the delta by 2, and the mean of the quantization error will be naturally 0. This can be calculated from this one here. That is the if mean of the En will be a integration from minus delta by 2 to delta by 2 E 1 by delta dE, and if after some manipulation we will find that it is equal to the 0 here. See here the mathematical calculation, and we are getting here the value of the 0. The variance or the power of the quantization error is here this will be the average value of the En minus modified En its square, and that will be the integration from minus delta by 2 to delta by 2 E square 1 by delta dE, and that will become the delta square by 12. This is the quantization error, which we have also discussed during the time of the PCM, pulse code modulation. The quantization error En and the quantized signal Xn are independent. They are not dependent function or the signals. En does depend on the quantized value of the and Xn, that is the Xcnt. But for reasonably complicated signals and for small enough delta, they are considered uncorrelated. What is the signal to noise ratio? As we know, the power related to the signal to the ratio of the power related to the noise is the signal to noise ratio. Now we will try to calculate the signal to noise ratio, that is the SNR, for this process here. As we know, the signal power is the sigma square, that is the xm by 4, its whole square, because xm is 4 times of the sigma. We have used the 4 here, the 4 sigma scaling. The quantizer error power is the delta square by 12. And now we are using the b plus 1 bits to store the quantized result. Then what will happen? The step size will become the minus xm to the plus xm, that is the twice of the xm divided by 2b plus 1. So xm to the power minus b. This is the step size. And then here what will be the error related to this quantization? Delta square by 12. So the delta square xm to the power minus b its square, that is the xm square to the power minus 2b divided by 12. This is the error here. And the signal to noise ratio, that is the 10 log 10 signal value its square, that is the xm by 4 its square divided by errors square, that is the xm square by 12 and multiplied by 2 power minus 2b, as we have calculated this value in this one. Now if we solve this one, then finally we will get it is equal to the 6.02b minus 1.25 dB. Now if we see, then we will find if we are trying to enhance the number of the bits during the time of the quantization, then what will happen? For each increment of the bits, there will be enhancement in the signal to noise ratio by the near about 6 dB. So here this is a formula. With the help of this formula we can calculate here the what will be the signal to noise ratio for the given range of the bits. And for each additional bit, we are getting here the 6.02 dB increase in signal to noise ratio. And for example, if we consider the 16 bit, that is the B is 15, then signal to noise ratio will become the 89 dB here. It would seem that changing the K sigma scaling of the quantizer will only change the 1.25 dB constant. But recall that we assume minimal overload error here. If we are changing here the k sigma scaling, then there will be change only in the constant, that is the 1.25 dB constant here. Now we have discussed the analog to digital conversion. Similarly, we can represent here the digital to analog conversion, and that will be can be represented something like in this manner, that is signal to noise ratio is S divided by N1 plus N2 plus so on, and this may be the signal to noise ratio for the digital to analog conversion. And we have also discussed the analog to digital conversion quantization error. Now we will moving towards the DSP calculation of the signal quantization effects. If we consider here the two numbers A and B of the 16-bit each, and say that this is the system here, and after the multiplication there is a need of the quantizer, because here the 16-bit information will be multiplied by the 16-bit another number, so it will become the 31. It has to be quantized to the required number of the bits. So after each multiplication there is a need of the quantizer here. See, and during the time of the representation we have to consider here the quantizer. There are two effects to be considered when we design a quantizer for multipliers and the accumulator. And what are these effects? The first, quantizer step size should be kept as small as possible, because due to this step size the quantization error will be, or the noise power will be lesser here. That is the value of the delta square by 12. So if the delta is smaller, the noise will be smaller. But and at the same time xm should be as large as possible. But these two are the contradictory statements here. So again there is a need of the trade-off between these two effects here. That is, the step size should be as smaller as possible, as well as we should try to enhance the range of the xm here. To calculate the noise power after filtration, we need to borrow some math here, and with some mathematical concept we can say that the Fourier transform of a random process doesn't exist, but the Fourier transformation of the autocorrelation function of a stationary random process exists, and that is known as the power spectrum density. So if we are trying to get the Fourier transformation of the autocorrelation of the random process, then that becomes here the power spectrum density. And the power spectrum density at the output of a filter is nothing but it is multiplication of the power spectrum density of the input and the square of the filter frequency response. That is, the if the xn is the input here, and power related to this one is the px e to power j omega, h e to power j omega, this is the transfer function or the system function. Then output power is the py e to power j omega, and that is equal to the whatever is the input power multiplied by square of the transfer function. That is, the power spectrum density at the output of a filter is the multiplication of the power spectrum density of the input and the square of the filter frequency response. H, Z is the system function, and when the Z is replaced by e to power j omega, it becomes the frequency response of the system or the filter. The noise power at the output of a filter is the integration of its power spectrum. So if we consider here the integration of this one, there is a sigma e square multiplied by 1 by 2 pi minus pi to pi h e j omega its whole square d omega. And if we apply here the Parseval's theorem, then we will find that 1 upon 2 pi integration minus pi to pi h e to power j omega its whole square d omega, it becomes the summation of the n is equal to minus infinity to plus infinity h n its whole square. So what is the delta here sigma f? That is the sigma s is the power spectrum density, uh, uh, noise power at the output of the filter. That is the sigma e square at the input side, sigma e square multiplied by n, ranging from minus infinite to the plus infinite, h n square here. So the output noise power can be calculated by either equation as an integral of the power spectrum density over all frequencies, or as a scaled infinite summation of the impulse response squared here. That is the impulse response squared here, this one summation, and multiplied by sigma e square. And the second one is naturally the easier for the purpose of the calculation. Now, if we consider this filter here, say this is the xn is the input and multiplied by the b, then there is a need of the quantization. Wn is the this output here, and yn is the final output. Then yn may be represented in terms of the wn, something like in this manner, and finally we can get here the transfer function of the system with respect to y and the w, that is the yz upon the wz, and it becomes the 1 upon 1 minus a z inverse upon z minus a here. Now, if we are interested to get the impulse response from omega n to the yn, then impulse response will become the inverse z transform of this one, that is 8 power n unit function of the n here. And next, the infinite summation absolute value, that is the hn square, it becomes the 1 upon 1 minus a square. Why we are trying to calculate this one? Because we have to find this one relation, that is what is the sigma f square. It is the sigma e square multiplied by hn square, having a summation from minus infinite to the plus infinite. And this second term is equal to that is the summation of the hn square, n is equal to minus infinite to the plus infinite. It becomes 1 upon 1 minus a square here. Now, if we calculate the noise power at the filter output, at the given filter output, then naturally it will become the 2 times, that is the sources here, it will be multiplied by 2 times. Here the delta square, that is the sigma e square here, multiplied by summation of the hn square. So this is the process by which we can calculate the noise power at the filter output. Now see, if we consider this example here, then the noise power at the filter's output is here the 2 times xm square 2 power minus 2b by 12, that is the delta square by 12, summation with the range from minus infinite to the plus infinite, h by x and its square, plus here 3 stages more, 3 stages having the 3 delta square by 12. This signal power at the output of a filter is usually expressed in this form, that is whatever is the signal input error multiplied by the hn square. This is the basic formula by which we can calculate the signal power at the output of a filter. In the scaling criteria, that is the second criteria, frequency response criteria. In this one, it assumes that we are putting a narrow band signal xm cos omega 0 n to the filter here. And in this one, if we are interested in order to avoid the overflow, then for that purpose, the value of the wn, it must be the whatever is the total value of the frequency response multiplied by xm, it must be less or equal to the 1 here. So from here we can get here the scaling factor s by this one here, that is the x maximum of the s is less or equal to 1 upon maximum value of this one, having the range of the omega 0 to pi h wx e to power j omega here. In the dynamic range, as we have discussed, the dynamic range of the floating point number system is larger. This is the advantage of the floating point number system, but the disadvantage is that during the time of the implementation, it becomes the more and more complex, and the designing becomes the designing is more hard than that of the fixed point number system here. Here we are coming to the last effect, that is the limit cycle oscillation. If the input is 0, and even then we are getting the output, that is the limit cycle oscillation. For example, if we consider a first order system, yn is equal to a yn minus 1 plus xn, and this is represented with the help of the block diagram in this form here. Then if we consider here the quantization of this one, then the quantization effect of this one, whatever is the quantized value of the a yn minus 1 minus a this is the actual value and this is the quantized value, and this must be less or equal to the half of the 2 power minus b. And this value may be again represented something like in this manner, that is the mod of the individual term, that is the first one quantized value, second one normal value, and difference of this one will be less or equal to 1 by 2 to the power minus b. And finally we will get that the if quantized value of the a yn minus 1 mod is yn minus 1 here, it implies that here the first value will become the yn minus 1 and the second one will become here the a yn minus 1 less than or equal to 1 by 2 to the power n. So the mod of the yn minus 1, it will become the 1 by 2 to the power minus b upon 1 minus mod of the a. Now see here, if we consider the example, say suppose that we use a 4-bit quantizer to implement a first order system and a is given 1 by 2 here. Then the dead band, what is the dead band? This is the dead band here, that is the mod of the yn minus 1 is less or equal to 1 by 2 to the power minus b upon 1 minus mod of the a. A is the coefficient of the first order filter here. So this value will become the 1 by 8. If the initial condition y minus 1 is given and it is equal to the 7 by 8, that is the 0.11, then what will be the output mod of the here the output yn, that is the ayn minus 1 here. This will become here the ay minus of the 1 first, when the n is equal to minus 1, it becomes the y0. That is, this is initially equal to the 0.00111, and because we are using this one with the help of the these bits here, and this may be approximated here, the approximate value or the rounding of this one may be represented as the 0.100. Now the next one will become the ay0, that is the whatever is the value of the a multiplied by the y0, it will become the y1, that is the y0 here will become the 0.11, and approximate value will be remain same. And similarly we can get here the y2, y3, y4. Then we will find that y2, y3, y4 are approximately same values here. So what is happening, even there is no signal, we are getting here the output, and this is named as the effect, that is the limit cycle oscillation effect here. Now if a is equal to 1 minus 1 by 2, similarly we can calculate here the values, and we can show what will be the effect of the this limit cycle oscillation here. So this is about the quantization, and it that has the 4 types of the trade-off, and in this one we have discussed the first effect, that is here what will be the effect on the quantization, and then effect on the signal. We have also covered the concept of the limit cycle oscillation in this lecture here, right? So if you will have any problem, then please discuss it. I think no problem. So we are So we are just stopping it.